Leah here from leahfirsci.com/MCAT, and in this video series we'll look at Fischer projections, starting with what they are and how to draw them, and then we'll look at how to convert between Fischer projections and Sohor's structures, Newman projections, and even Haworth structures for sugars. You can find my entire series along with a Fischer projection practice quiz and cheat sheet by visiting my website leahfirsci.com/Fischer. Fischer projections were introduced by Dr. Emil Fischer, who was studying carbohydrates and needed a simpler way to represent these complex chiral three-dimensional molecules. Imagine that you're working on these reactions and drawing them again and again. If I had to draw this structure again and again, I would lose my mind. But if you look at something like this, it's simpler, it's got clean lines, and it makes it much easier to study and much less confusing. But Fischer projections don't apply only to sugars. You can use them to represent all sorts of chiral molecules. We'll start with something as simple as a molecule with one chiral center. Recall that in order for a molecule to be chiral, it has to have an asymmetric center, which is typically going to be a carbon atom. The hybridization is sp3, which means it's tetrahedral and three-dimensional, and it has to have 4 unique substituents. For this example, we'll just use letters A, B, D, and E, where the central carbon is the chiral carbon. To represent this molecule as a Fischer projection, all we have to do is draw a cross, where the lines going up and down represent groups going into the page, and the lines to the right and left represent groups coming out of the page. Let me show you how to convert it, and then I'll show you how to read it. Converting is a little tricky when you're given a standard structure, so you want to rearrange your molecule so that your three-dimensional structure shows the groups on the right and left coming out of the page and the groups up and down going into the page. In order to do that, we have to get creative, and we're going to take the molecule starting at A and spin it. Almost imagine that this is a closed book where D represents the top of the book and B represents the bottom, and you're grabbing the top page, the cover, D, and opening it in this direction. By doing so, imagine that D comes from the right, up towards you, and then towards the left, but it's still facing up and out of the page. In the process, we're also moving it slightly upward, so it's still out of the page, but now it's horizontal instead of pointing down. In the process of pulling D, B got pulled forward, and that means instead of pointing into the page, it now points out of the page. And remember, since we tipped the molecule slightly upward so that D went from somewhere below the carbon to the level of the carbon, anything on top got pushed back, and that means A got dumped into the page. So we show that with dashes for A going into the page. And finally, E also got pushed slightly down, and that means E is also going into the page. And this is the structure that you want to imagine when you see a simple cross with a substituents around it. As you can see, all we did was take the structure, flatten it out, so we got rid of dashes and wedges, but hidden in that Fischer projection is still the idea of wedges horizontal and dashes on the vertical. So looking at the Fischer projection, again, here's what you want to recognize. The central carbon, the carbon in the middle of your cross, that is your chiral carbon. That's where the substituents are attached. Anything on the horizontal is coming out of the page to the right and left. Anything on the vertical is going into the page. A goes into the page on top of the molecule, and E goes into the page on the bottom of the molecule. When students look at a Fischer projection, they often confuse, is it horizontal wedges or horizontal dashes? Let's explain it using the amino acid L-alanine as an example. We have a carboxylate on top, an NH3 plus on the left, hydrogen on the right, and then the alanine R group, which is a CH3 on the bottom. A lot of students see this and then they get confused. Is it horizontal wedges and vertical dashes, or the other way around? The correct way to represent this molecule is a central carbon with a hydrogen atom forward on the right, NH3 plus forward on the left, and CO2 minus and CH3 going into the page, top and bottom. What you don't want to draw is something like this, where your carboxylate and your methyl come out of the page on the vertical, and the hydrogen and the NH3 plus go into the page on the horizontal. And a good trick to remember this is to picture this guy. This here is Mr. Organic Chemistry, and he's so excited to join our video that he came dressed in a bow tie. And notice that with a bow tie, it's horizontal wedges. That means the horizontal is coming out of the page. And you can imagine that the vertebrae and his spine, that goes up and down, and that goes into the page. That is how you want to remember the structure of the amino acid. And yes, it is very important, because not only is this structure incorrect, it's actually the enantiomer of the molecule we started with, and the enantiomer of L-alanine is D-alanine, which is a completely different structure. Watch what happens if we put them side by side. The chiral carbon hasn't moved, and the substituents are oriented the same way around each one. But if I were to superimpose them, they would be exact mirror images, because for every substituent going into the page for L-alanine, it comes out of the page for D-alanine, and if it comes out of the page for L-alanine, it goes into the page for D-alanine. When you have two molecules that are chiral, have the same exact substituents but opposite orientation, they are enantiomers. And this is critical to a biological system where proteins and enzymes are very specific to the structure they recognize. If they're looking for an L-alanine, they will not recognize a D-alanine, just like a right-handed glove will not fit your left hand because they are not superimposable. And let's prove this by finding RNS for each molecule. We'll start with D-alanine, where our substituents are prioritized nitrogen, number 1, carbon with an oxygen is number 2, carbon with hydrogen is number 3, and hydrogen is number 4. We get rid of the lowest priority substituent, number 4, and then trace the path from 1 to 2 to 3. Since the top of the path goes to the right, this is R. And now we'll do the same thing for L-alanine. Nitrogen is number 1, carboxylate number 2, methyl 3, and hydrogen 4. When we cross out number 4 and trace the path from 1 to 2 to 3, it looks like it's also R. But in order to have an R, number 4 has to be in the back. If number 4 is coming out of the page, we have to reverse the chirality because we have to imagine we're looking at it from the other side. And that means L-alanine is S, where D-alanine is R, proving once again that these two are enantiomers. Here's another concept you want to consider with Fischer projections, and that is what happens when you do a 90-degree rotation. Let's do a simple molecule where our substituents consist of an OH, a CH3, a hydrogen, and a chlorine. What happens if we take this molecule and rotate it 90 degrees clockwise or counterclockwise? You'll get the same thing. So that we now have OH to the right, CH3 down, hydrogen left, and chlorine on top. It looks like they should be the same, but they are actually enantiomers of each other, and I'm going to prove it. Let's draw out the three-dimensional version of this molecule. So we have CH3 and Cl coming out of the page. We have hydrogen down into the page and OH up into the page. That's our first structure. Now let's see what happens with the second structure. But first let's change the color to make sure we can tell them apart. We'll start with the central carbon, but now we have the OH coming out to the right, hydrogen coming out to the left, the CH3 is down into the page, and the chlorine is up in the page. If we're trying to figure out the relationship just by looking at it, it's hard to tell because the substituents are not lined up correctly. So we have the option of finding RNS, or we can rotate this molecule exactly as we see it. Because it's not in a Fischer projection, I can rotate it as much as I want because molecules can rotate in space, and this is a three-dimensional molecule. I'm going to rotate it 90 degrees counterclockwise so that the atoms all line up. Once again, we have a central chiral carbon. Now we have the OH coming up and out of the page. Because again, I'm keeping the dashes and wedges, I'm simply turning the molecule 90 degrees. I have the chlorine left and into the page, hydrogen down and out of the page, and methyl right and into the page. Take a look at these two structures. They're oriented the same way around the chiral carbon, but where the purple structure comes out of the page, the green structure goes into the page. Where the purple goes into the page, the green goes out of the page, and that means they are enantiomers of each other. So how did that happen? Well, if the Fischer projection represents dashes and wedges, and you rotate it 90 degrees, you're swapping all your dashes and wedges, getting the exact mirror image. But if you take that Fischer projection and flip it upside down, then you have 180 degrees, meaning it's the same exact thing. Because 0 degrees is your starting molecule, 90 is the enantiomer, and 180 degrees is the enantiomer of the enantiomer, or simply your starting molecule. As you're studying Fischer projections in organic chemistry and biochemistry, you'll see more complex molecules that have multiple horizontal lines and your one vertical. We treat it the same exact way and read it the same exact way. For this structure, we have 2 chiral carbons, and the substituents coming out of the chiral carbons will be out of the page for the horizontal and into the page for the vertical. That means we can take the structure and just put wedges on it like this. Any lines on the structure represents bonds between carbons, and if it ends in a line, that's a CH3. So for example, here we have a methyl group, here we have a methyl group, and we can choose to put substituents on it. What this will look like is a bond between your 2 chiral carbons, a methyl group going into the page on the bottom, a methyl group going into the page on top, and then methyl groups coming out of the page both on the right and the left. And the same thing applies if you have even more chiral carbons. For example, here we have 3 chiral carbons. Everything on the right and the left is coming out of the page, and anything on the top and bottom is going into the page. But your test questions will likely have you look at molecules that are not in Fischer projection and have you convert them, or Fischer projections asked to compare to something else. So you understand Fischer projections, but now how do you find chirality if you have 1 chiral center, 2 chiral centers, or more? That's exactly what we'll be covering in the second video, which you can find along with the entire series on Fischer projections, the Fischer practice quiz and cheat sheet by visiting my website leahforsci.com/Fischer.